Hi, greetings of the day. Welcome to my channel Cumulonimbus AI. My name is Vidya. Today we are going to discuss about implementation of hash table to demonstrate constant complexity using Golang. Consider a use case where we have a basket full of mixed fruits placed on the floor. Now, our goal here will be to find if the fruit asked for is available in the basket or not. For this, we shall create a hash table, essentially an array of strings that can hold names of the fruits. The index to the fruit will be the first character of the fruit's name in ASCII value. This index is generally referred to as hash value. We directly compute the hash value from the given input string for searching basket and directly map the same to the index. If found on comparison, we report as found, otherwise not found. Now we are going to demonstrate computation of algorithmic complexity mapping on the constant value. We will understand more as we key the implementation and grab the results. Now we go ahead and declare package main as usual for every Go programming. We will import fmt, generally used for logging and printing. And then we declare the function main, which is the entry point for the application. We further go ahead and create the hash table, which is array of strings. Where fruits 256 string, and then we further also take an input string which we are expected to search in the basket. Now we go ahead and initialize the fruit basket with mixed fruits. So here we are going to fill in fruit, apple. The ASCII value for A going to be 97, and so I put here. Further, add some more fruits. Orange. The ASCII value is going to be 111. Fruits. Pineapple. That's going to be 112 for character P. So the values that you see here, 97, 111, and 112, are generally referred to as the hash value that maps to the index of the table. Fruits equal to grapes, fruits equal to mango, fruits equal to kiwi. I'm just filling up the basket with multiple mixed fruits. Strawberry, fruits equal to banana. Okay, we have about more than half a dozen fruits here, so we'll go ahead and fill the index. This maps to G maps to 103, mango maps to 109, kiwi will be 107, strawberry will go into 115th slot, then banana will be 98. Further, we seek input from the user for searching into the basket. So we take, enter the name of the fruit you want to search in the basket. And then we take the input fmt dot scanf percentage yes comma input. We further compute the hash value. Compute the hash value. Hash val equal to input of the string at 0th index. Now we compare the hash value on a given index across the hash table and verify if the input string is found in the basket. If input equal to fruits of hash val, then we say fruit is found. Fruit percentage yes is found in the basket. Otherwise, we'll say fruit not found is not found in the basket. And then simply return. We save this file and all set for building it. Now before running this code, let's go and perform some sanity checks. I may want to give a new line here before accepting the input. Okay, there's a typo here. This needs to have double quotes, that's missing. Here is a double quotes that's missing. And here it's printf, not println. Okay. Fine, looks good. We'll save it. Go ahead and build it or run it. So we have kiwi here. Let's see if it's able to identify. Yeah, kiwi is found. Let's run it once more. Rips is found. Once again, apple. Good. How about uppercase apple? Uppercase apple is not found, and that's reasonable because it maps to lowercase ASCII character 97, and in case we had converted uppercase apple to lowercase, it would have been identified. However, now we have been successfully able to demonstrate the implementation of hash table and look up for particular fruit in the hash entry given the index of the first character of the fruit mapping to the slot given here. So the complexity here is 1, and that maps to complexity of constant value big of O1. Now if we were to optimize this code, we could go ahead and look into possible optimization pathways. One such optimization that I could think of is because we were not able to identify uppercase, we would go ahead and convert the input string to lowercase and then feed it for comparison. So if we were to convert the input string, convert the input search string to lowercase, irrespective of the input, then we would just call upon string dot to lower input and capture that into another variable, say find me. To cover that, go ahead and include package strings. Now instead of input, we'll use find me and then use find me in the comparison. So now in this case, if apple was fed with uppercase, it would be converted to lowercase here, and the first character would be mapping to lowercase a, and then we compare that with the hash table on the given index. Now we should be able to find apple. So just save it, then run it again. This time we should be able to find result that says apple is found. Yeah, good, apple is found. It should also be able to identify cases where we have full uppercase apple. Good. Partially uppercase. Okay. So this is one interesting optimization that we have made. Further, if we were to think of optimization, then we will go in direction of working towards reducing the size of the hash table. Here the size of the hash table is 256, while the number of characters, alphabetical characters mapping to the fruits is just 26, assuming that every character maps to only one fruit. In order to remove the redundant entries in the hash table, we'll go and introduce some constants. Constant alphabets int equal to 26. We'll use this alphabet over here, which will define the size of the hash table. Okay. Now, in order to manage the index over here, we will need to hop the offset by ASCII value. So we say ASCII start int equal to 97. So let's assume that we are going to dump fruit names starting from A to Z in small letters or lowercase. We have ASCII start here. So we take ASCII start as the start of the index and then go ahead and subtract that. So this will be the start of the index on the fruits hash table. It means that if we were to find apple and A starts with ASCII 97, we would end up having an identifier at slot 0 in the fruits table. Similarly, for orange, it would be 111 minus 97, it will be at index 14. So we just subtract that over here and then convert it. Okay, we save it. Now we go ahead and again run this application. So if I were to search kiwi, I should find it. Yeah, kiwi is found. Strawberry should also be found. Yeah. STRAW in uppercase. Berry should also be found because we have optimized it to take uppercase characters and then convert them accordingly and then map to the hash table. Uppercase apple should also be found. Yeah. Mangosteen is the only thing that is not found. So just go ahead and verify. Yeah, we don't have mangosteen in the hash table. So with this, we have been able to arrive at performing a lookup of a fruit on search into the hash table that we have built with just direct mapping into the slot. The complexity that we have observed here is of one which is generally referred to as constant complexity. And that's it. Thanks for watching.